Hey everyone, and welcome back to The Explainer. Today, we're doing what we do best, decoding medical research. We are diving into Lesson 6 of Evidence-Based Medicine for Techies, focusing on prognosis and harm studies. Now, if you're just joining us for the first time, this whole explainer is built on the Vibrance philosophy. What does that mean? Well, it's all about guided discovery and Socratic learning. We're taking the incredibly complex world of clinical evidence and translating it into the language that you, as techies, already speak fluently. Think of it as a fast, jargon-translated map of the entire clinical world. So grab a coffee and let's get into it.
Okay, let's dive into this. Here is our roadmap for today's toolkit-based investigation. We're going to cover 5 key areas. First, when RCTs fall short. Second, cohort versus case control studies. Third, we're decoding the hazard ratio. Fourth, catching the confounders. And finally, the patient at the center. Starting us off, Section 1. When RCTs fall short. So think about this like an engineering problem. In software dev, you wouldn't use a front-end framework to optimize a back-end database, right? No way. You need the exact right tool for the specific job. Medical research is literally exactly the same. Every study design has a specific use case. To truly understand clinical research, you really have to know when a tool is being pushed way past its limits. Which brings us to a huge, fundamental question. If randomized controlled trials, or RCTs, which are basically the clinical equivalent of our A/B tests, are considered the absolute gold standard of evidence, why do they feel so badly at evaluating long-term risks and rare harms? Just take a second and think about that. Why would the most rigorous, heavy-hitting tool we have suddenly become the completely wrong choice?
Well, here's the reality of the situation. RCTs give us incredible precision, absolutely, but they have some major, glaring limitations when it comes to time and scale. First off, they're often just way too short-term. I mean, you might run a beautifully controlled trial for 6 months, but what happens if a severe harm takes 5 years to show up? You're completely blind to it. Second, the sample sizes are usually way too small to catch rare side effects. If a complication only happens in, say, 1 in 10,000 patients, an RCT with 500 patients is going to miss it almost every single time. It's just a numbers game. And finally, these highly controlled trial environments, they just don't reflect real-world usage at all. In a trial, patients are screened, they're constantly monitored, and they're nudged to follow protocols perfectly. But in the real world, come on, people miss doses, they have overlapping health conditions, their environments are totally unpredictable. So when we need to investigate rare harms or long-term prognosis under actual human conditions, our supposed gold standard A/B test is fundamentally the wrong tool. We have to pivot. We need alternative tools. Let's move to Section 2 and see how this builds. Cohort versus case control studies.
Because we obviously can't run massive, decade-long A/B tests on humans, we have to rely on observational designs to build out our toolkit. This is how we track down those elusive long-term risks. And the two absolute heavy hitters here are cohort designs and case control designs. The big juxtaposition to remember here is their direction in time. It's all about directionality. Cohort designs look forward. You start with a group of people and literally follow them into the future to see who gets sick. Case control designs, on the other hand, look backward. You're basically playing detective. You start with patients who are already sick and you investigate their history to figure out what they were exposed to in the past. It's a completely different approach, but both methods are incredibly powerful ways to gather data when a controlled experiment just isn't going to happen. And this brilliantly illustrates how a cohort study flows chronologically. Imagine starting at year 0. You assemble a nice, healthy group of people, and maybe some of them have a specific exposure, like a brand new lifestyle habit, or maybe they're taking a long-term medication. Flash forward to year 5, you're monitoring that exact same group for any initial symptoms. And then, by year 10, you log exactly who developed the specific disease or harm. Notice we aren't intervening at all. We are simply letting time run its course and tracking the data logs as they naturally generate over a full decade.
All right, moving on to Section 3, decoding the hazard ratio. So once we run these massive, lengthy studies, we get data, lots of it. But as techies, you know better than anyone that raw data is completely useless if you don't know how to read the output metric. Just like you need to understand server metrics to monitor your system health, you have to understand clinical risk metrics to evaluate patient health. The definitive metric here is the hazard ratio. Let's break this down into plain English. A hazard ratio is basically a measure of how often a particular event happens in one group compared to how often it happens in another group over time. Did you catch that? Over time. That is the absolutely crucial phrase. Other metrics might just give you a static, frozen snapshot of risk, but the hazard ratio bakes time directly into the equation.
It tells us the speed at which the hazard is hitting our exposed cohort versus our control cohort. Whenever you're assessing long-term harm, this is the key output you'll be looking for.
Which brings us to Section 4, catching the confounders. Here's the catch with observational studies. Because you aren't strictly controlling the environment like you do in an RCT, your data is going to be noisy. In medical research, this noise is called a confounder. Think of a confounder as a highly critical bug in your dataset that is just totally skewing your signal. Debugging this requires a really systematic approach. First step, you identify a potential relationship in your dataset. Okay, looks interesting. Next step, you go hunting for that confounder, that sneaky outside variable skewing the signal that you might have missed initially. And finally, step 3, you statistically adjust the data to isolate the true cause and effect. Listen, if you don't aggressively hunt down and isolate these hidden variables, your final analysis is going to be completely, confidently wrong. Now, what's really interesting about this slide is it ties back to a reoccurring theme throughout this course. We call them the 8 moments where the numbers surprise you. These are the most counterintuitive, mind-bending results across the entire curriculum. And you know what the biggest reason is for those numbers totally surprising you? A missed confounder. A single missed confounder can completely flip your assumptions about a dataset upside down. It can literally make a safe drug look dangerous, or, even worse, a dangerous intervention look perfectly safe. It's a huge wake-up call. It reminds us why we have to be absolutely meticulously rigorous when we review observational research, and why we can never, ever just blindly accept the raw data at face value. And finally, Section 5, the patient at the center. So we've talked a lot today about cohorts and hazard ratios and debugging messy datasets, but we absolutely cannot lose sight of the most important element of all of this. These statistics, these numbers on a screen, they represent real people. And I think this is captured so beautifully in the course syllabus. It says, critical appraisal and evidence-based medicine, taught the way a clinician actually thinks, starting with a patient, not a p-value. So the crucial point is that this is the core ethos of the entire curriculum. Whether you are hunting down a 1 in 10,000 side effect, or trying to figure out if a study properly adjusted for its confounders, or you're acting as an LLM-assisted research assistant just screening abstracts, you're doing it because there is a living, breathing human being at the end of that data pipeline. We always start and we always end with the patient experience. That philosophy right there is what ties all these complex technical lessons together. Which leaves us with this final, really important question to ponder. If a p-value isn't the starting point, how are you going to reframe your next data investigation to put the human impact first? I want you to take that patient-centric mindset with you as you tackle the rest of the course, and as you apply this kind of evidence-based critical thinking to your own analytical work. Thank you so much for joining me on this explainer, and I will catch you next time.